So here's our roadmap. First, we'll size up the challenge, the loads and stresses that are trying to tear our footing apart. Then we'll do a bending moment analysis to map out exactly where the weak points are. With that intel, we'll calculate the steel needed for both the top and the bottom, and finally, we'll put it all together into the final design blueprint. Let's get started.
Okay, first things first. Before you can solve any engineering problem, you have to truly understand it. And in structural engineering, that means getting a handle on every single force that's in play. So here's the situation. You've got the incredible weight of a building pushing down through these three columns. We're talking over 1,000, then 1,600, then 1,200 kilonewtons. That is a lot of force. But at the same time, the ground itself is pushing back up with a constant pressure of 351 kilonewtons for every single meter. So our footing is literally caught in the middle of this huge tug of war. The big question for us is, what do we design to put in that space to make sure it doesn't just snap in half?
You know, the secret really lies in this amazing partnership between two materials. Concrete, on its own, is an absolute beast when you try to crush it. It has incredible compressive strength. But if you try to pull it apart, to stretch it, it fails really easily. It has terrible tensile strength. And that is exactly where steel comes in. Steel is fantastic in tension. So by embedding steel bars, or rebar, inside the concrete, we create this perfect team that can handle both squeezing and stretching. Our job now is to figure out precisely how much steel we need, and just as importantly, where exactly to put it.
So how do we find those spots where the footing is being pulled apart? We need a map. And in our world, that map comes from something called a bending moment analysis. This is going to give us a crystal clear diagram of where the stresses are the absolute highest across the entire footing.
Take a look at that red curve down at the bottom. That is our stress map. We call it the bending moment diagram, and reading it is pretty simple. Wherever that line peaks, whether it's way up in the positive or way down in the negative, that's a point of maximum bending. Those peaks are the critical danger zones, where tension is trying its hardest to rip the concrete apart. This map tells us exactly where we need to concentrate our steel.
And this map shows us two major hotspots. First, we've got this huge negative moment, negative 1,366 kilonewton meters. Now, negative in this context just means the footing is trying to bend up like a smile, which puts the top surface in tension. Then we see a maximum positive moment of 937 kilonewton meters. That's where it's trying to bend down like a frown, creating tension at the bottom. Just looking at the numbers, you can see that the negative moment is way, way bigger. That's our number one priority.
All right, we have our primary target, that massive negative moment of 1366. Now it's time for the cool part, translating that raw force into a specific amount of steel. The key number we're trying to find here is called ρ, written with the Greek letter R. It's simply the reinforcement ratio. Think of it like this. What percentage of the concrete's cross-section needs to be steel for it to be strong enough? That's what ρ tells us. And this is the tool we use to find it. I know this formula might look a little intimidating at first glance, but its job is actually really straightforward. All it does is balance the forces we know, the strength of our concrete and steel, against that big bending moment we found. We just have to plug in our values, and it will spit out the exact ratio of steel we need, our value for ρ.
Let's just walk through what we're plugging in. First is M, our bending moment. Then B and D, which are the physical dimensions, the width and effective depth of our footing. And finally, F'C and Fy, which are just numbers that represent the known strength of our concrete and our steel. So we put all these knowns into the formula, it does the math, and it solves for our one unknown, ρ, giving us a required steel ratio of 0.0053.
Okay, but what does that number, 0.0053, actually mean? This is where we turn that abstract ratio into something a contractor can actually build. We multiply our ratio by the concrete area to get a required area of steel, or AS, which comes out to 3,362 square millimeters. And in the real world, that means for every single meter of our footing, we need to place 9 bars of 22 millimeter diameter steel. See that? We just turned an invisible force into a concrete building instruction.
Great, top steel is done. Now let's tackle the bottom reinforcement. We're going to follow a similar process, but we're about to run into a really interesting quirk of engineering, where a totally different rule takes over.
So before we even start the calculation, we have to talk about something called minimum reinforcement. All the engineering design codes say you have to include a certain minimum amount of steel in any concrete structure, period. And this isn't just for handling big loads. It's there to control tiny cracks that can form from things like temperature changes or the concrete shrinking as it dries. It's all about long-term durability.
Now check this out. When we run the same formula for the bottom reinforcement, using that much smaller positive moment, we get a really interesting result. The amount of steel the formula says we need is actually less than the minimum amount the building code allows. So what happens? The code wins. The stress here is so low that our main concern isn't breaking, but rather controlling those little shrinkage cracks.
You can see the moment M here is tiny compared to what we used for the top. The code says, I don't care what the stress is, you must have a minimum steel ratio of at least 0.0018.
So we completely ignore our smaller calculated number and use the code's minimum instead. That gives us a required minimum area of steel, or AS-min, of 1,260 square millimeters. In this case, the code is designing this part of the footing, not the forces.
So for the bottom of the footing, the code is calling the shots, not the bending stress. And that required area, 1,260 square millimeters, translates into a very practical spec: 8 bars of 14 millimeter diameter steel for every meter of the footing.
Okay, we've done the analysis. We've crunched the numbers. We've checked it against the building code. Now let's put it all together and see what the final blueprint actually looks like.
And there it is. This drawing is the direct result of everything we just did. You can see the specs written right there on the plan. At the top, to fight that huge negative moment, it calls for 9 phi 22 per meter. That literally means 9 bars with a diameter of 22 millimeters every meter. And down at the bottom, where the code took over, it specifies 8 phi 14 per meter. We have successfully turned a complex analysis of invisible forces into a simple, buildable design.
So, we've nailed the calculation for the required steel. But of course, the engineer's job isn't quite done. They still need to think about other crucial details, like specifying the concrete cover. That's the amount of concrete over the steel to protect it from rust, or the exact spacing between the bars. It's a great reminder that great engineering is always a balance, not just solving for the big forces, but also considering all the practical details that make a structure safe and durable for decades to come. Thanks for digging into this with me.